So spatial pulse length is one of the parameter of the pulse wave ultrasound that's determined by both the source and medium. Though other parameters, pulse duration, pulse repetition frequency, pulse repetition period, and duty factor, all of them are grouped together because they got one thing in common. They are all determined by the source. Now these bottom three have something in common. Out of these four, these bottom three has something in common, and that's it changes with the imaging depth. How far deep down that thing affects these three parameters, right? So it changes with imaging depth. Now what's that supposed to mean?
The deeper.
The deeper, the longer,
Closer.
the superficial, the closer, the lesser. But it doesn't affect the pulse duration. But it does
No,
affect.
the frequency, yeah.
It does affect. So that means that changes when the depth of penetration changes. Like I'm scanning pancreas, which is superficial. So I'll have a different PRP, PRF, and duty factor. But when I change my depth of view, and now I'm imaging the kidneys, which are right here, posterior, right? So it has to cover all this ground, and that means that that's another way of saying that there's a change in my imaging depth, right? It was superficial, now it's deep. That will affect those three bottom parameters, but not the pulse duration. Right?
Right.
Clear? Okay. But how would that affect? That's the next question, right? Then these two have one thing in common. These two parameters, the pulse duration and the spatial pulse length, have one thing in common. As these three bottom parameters changes with the imaging depth, these two do not change with the imaging depth. Do not change with imaging depth. What is that supposed to mean? No matter how far deep down you go, no matter how superficial you are, but these two parameters or five parameters don't get affected. That's it. And that's the reason why they group like that together, so that it will be more easier to memorize these facts. Okay? So a pulse. We got a couple of up and down, and then we got a flat line. Right? Now let's dissect the anatomy of this. So what is this? The on time? It's that time when the pulse is being transmitted, or the transmission time, right? We don't get any transmission here. This is the off time, or the listening time, or the receiving time. We know that, right? So it's that time when the pulse is actually on, or transmitting, right? Or talking. So that time when the pulse is actually on, starting from here till that time when the pulse is off, this time is called your pulse duration. right? So it's something that is predefined by the manufacturer. Is it adjustable? No.
No.
Pulse duration is not adjustable. Who determines pulse duration? Pulse duration is determined by
Source.
wonderful source. So it's non-adjustable and it's determined by the source. It's that time when the system is actually transmitting, or is that time when the system is on, or it is the talking time. Now, how is a time expressed in units of time, right? Seconds, microseconds, milliseconds, megaseconds, right? So this is expressed in unit of time, which is seconds, microseconds, or milliseconds, but anything that has got to do with time. Okay? And it's not adjustable. It's something that's predefined by the manufacturer. For diagnostic sonography, we use the range between 0.3 to 2 microseconds. 0.3 till 2.0 microseconds. That's ideally used in diagnostic medical sonography.
What, could you say that again?
That time frame of transmission is used in diagnostic modalities. So our pulse duration of range between 0.3 to 2 microsecond is ideal for diagnostic purposes. So if you break this thing, further dissect it, then it looks like the pulse duration is dependent on two things. How many cycles are present, right? So that means number of cycles. The longer, the more the number of cycles, the longer the pulse duration, right? And period of an individual cycle. Two factors. Period of individual cycle. Right? What does that mean now?
The period of the individual cycle is one of the up downs.
Wow. Wow. Very good. The shorter the up down, the smaller the period. The longer the up down, the greater the period. So pulse duration would be ideally few cycles with less periods. You get
Wish
it?
I had a few cycles with experience too.
You see how we're manipulating the word? So this is times is equal to pulse duration. So pulse duration is the number of cycles. So these are the cycles. So we got 1, we got 2. Number of cycles and the pulse times the period of individual cycles. What kind of cycles do we need for diagnostic medical sonography? Fewer number, shorter period of individual cycle. Now we know period is in inverse relationship or indirect relationship with the frequency. So pulse duration is directly proportional to PD is directly proportional to the number of cycles. We know that. Number of cycles. Then pulse duration is directly proportional to period of individual cycle. But we do know the period and frequency are inversely related, so pulse duration is inversely related to frequency. Does that make sense? Now, what is the difference between a long pulse and a short pulse? This is a long pulse. 1, 2, 3. Right? What makes it long? Many cycles. Cycles in a pulse. What makes it long? The other factor, individual and cycles. Individual cycles with longer period. Individual cycles with longer periods. Then comes another thing, which is the short cycle. So now we have 1, 2, 3. Oh, what makes it a cycle short now? Look at the number of cycles. So fewer cycles,
Short period.
and individual cycle with
Shorter.
shorter period. Thank you. Individual cycles with shorter periods. That's the difference between a short pulse of cycles and a long pulse. Is that visually understood? In clinical imaging, we usually use 2 to 4 cycles. Like this is for the clinical imaging. In clinical imaging, two to four cycles. Okay. Now what's the spatial pulse length? It's the distance that the pulse occupies out there in the space. That's what a spatial pulse length is. Like for instance, this is a pulse with fewer cycles. It's being transmitted out there in the space, right? Will that occupy more distance, or would that occupy more space, or something with more cycles with longer period of an individual cycle? Shorter, less space, longer, more space. So what is spatial pulse length? Is that space of the distance a pulse occupy out there. What's the unit of spatial pulse length? Spatial pulse length? It's basically the space pulse occupies, right? That's a spatial pulse length. Okay, now what is it determined by, the spatial pulse length? Think about that image.
How many cycles?
What determines spatial pulse length?
So centimeter?
Okay, so it's determined by both source and medium. Is it affected by the imaging depth?
No.
Spatial pulse length and pulse duration are the two factors that are absolutely not affected by the imaging depth, right? So, again, let's break it down. This is the spatial pulse length. So, spatial pulse length, it's the length, right? So, spatial pulse length is directly proportional to the number of cycles in the pulse. The greater the number of the cycle, the longer the pulse, the greater the spatial pulse length, right? The longer the pulse, the greater the spatial pulse length. So my next question is, what makes pulse longer? More cycles? Individual cycle with longer period? That would make a long pulse. What makes a pulse short? Fewer cycles. It's cycles with individual smaller periods, right? So that means if I would say that spatial pulse length is directly proportional to the number of cycles, would that be right?
I'm sorry.
If I say that spatial pulse length is directly proportional to the number of cycles, the greater the number of cycles, the greater the spatial pulse length.
Yes.
Right. Okay. Let me write that down. So SPL spatial pulse length is directly proportional to number of cycles. Okay. What else? Then SPL is directly proportional to the wavelength of these cycles. SPL is directly proportional to the wavelength of cycle. Now what is that supposed to be? Wasn't that the period? It wasn't the period. Period is 2 hours from here to Houston. Wavelength is 200 miles from here to Houston.
Oh, it's just the same with
It's
different,
the same, but expressions
different way of measuring.
different way of measuring. There you're using time as a source of measurement. Here you're using distance as a source. So, spatial pulse length is directly proportional to the wavelength of the cycle. The longer the wavelength, that's another way of saying longer period too. But period is expressed in terms of time. This is expressed in terms of distance, right? So, spatial pulse length is directly proportional to the number of cycles, right? Spatial pulse length is directly proportional to the wavelength of cycles. But wavelength and frequency have an inverse relationship, so spatial pulse length is inversely proportional to the frequency. Is inversely proportional to the frequency. Okay. Again, long and short pulses. Two characteristics produces longer pulses. What were those two? Oh, ouch. What were those two characteristics? The number of cycles in the pulse and the period of individual cycles. So let me replace that word period with the wavelength. So it's the same, longer pulses. So let me add 1 point more to it. Individual cycles with longer wavelength.
Yes.
Individual cycles with shorter period, fewer cycles. Third thing, individual cycles with
Shorter wavelengths.
shorter wavelength. Is this concept clear? What makes a pulse long? What makes a pulse short? How does these parameters comes into place? Is this adjustable?
No. Ah. Pulse duration and only pulse frequency, period, and power. So yeah, the period. So yes, it is adjustable. Big parameters are all adjustable. Frequency, power, intensity.
Spatial pulse length is not adjustable,
So wavelength, no, it's not.
right?
Correct.
Nor is pulse duration. Because this is what a spatial pulse length is. If this is a
Determined by the
pulse,
transducer, right?
you see this pulse? then what is the spatial pulse length? From the beginning of the transmission to the end of transmission. This alone area is spatial pulse length. SPL. No, it's not adjustable. Now let's come to PRP. What is a PRP? Pulse repetition period. So if this is a pulse up, down, PRP, as they say, changes with the imaging depth. Now what's that thing that changes with the imaging depth? PRC, PRF, unique factor, right? PRC, PRF, they change with the imaging depth. Alright, so what is PRP? PRP is from the beginning of the pulse to the beginning of the next pulse. So what does it include? Both the on and the off time. The on time and the off time together makes a PRP, which is expressed in unit of time, which is seconds. So let me ask you this: if I'm imaging the pancreas, which is right here below my Xiphi sternum superficial position, right in the midline, would it take more time to get to the pancreas and come back, or would it take more time to get to the kidneys and come back, which are right here in the posterior abdominal wall? Kidneys. So wouldn't it not lengthen my listening time? That's why PRP changes with the imaging depth. If it's if it's scanning something superficial like pancreas, then we have a lesser listening time because it's going to go strike that desk and come back to that podium, right? But if it has to go all the way to the back and strike the wall and then come back, as if I'm imaging the structure which is situated deeper in the body, like the kidneys, it will take more time. What lengthens? What lengthens? The on time? No.
Oh.
Or the off time.
The off time?
PRP is a combination of both the on and off time. So if one of the parameters of those two, one of the factors of those two, of that parameter is increased, which is the listening, it will affect the PRP. So longer PRP with structure situated deeper in the body. Shorter PRP with structure situated more superficial in the body. Since PRP includes both the on time and the off time, and the off time is affected by the depth of imaging, there will be a lesser on time if we are scanning some structure which is superficial. There will be a longer off time if we are scanning some structure which is deep. So that's how depth of imaging affects this parameter. Does that make sense? Claire? You change the imaging depth, you change the PRP. You're scanning the pancreas, which is superficial, and now you're scanning the kidney, which is deeper. So what did you change?
Imaging depth.
Imaging depth. And you have the capability to change it so it is adjustable. PD is not adjustable. Spatial pulse is not adjustable. That's how it becomes adjustable, because it comprises of both the talking and the listening time, the on and the off time, the transmission and the receiving time. And receiving time varies depending on the depth of view, superficial, lesser, deep, more, that's how it affects the PID. Same thing applies for PRF. Where did it go? PRF. So pulse repetition frequency. PRF now. Again, one of those parameters that are affected by the depth of view. So it is basically, pulse repetition period is the number of pulses that an ultrasound system transmits in the body each second. Number of pulses. Say I got 1, 2, 3 number of pulses that I'm emitting or transmitting in per second. Right? See it. See it. What is it determined by? The PRF?
Imaging data.
No, it's determined by the source.
Source. It's affected by the imaging, right? How does it get affected? When the depth of view increases, what happens? The number of pulses that were being,
Isn't it indirectly related?
it's indirectly related.
Yeah, so if
So when
depth
the
increases, it
The
shrinks.
PRF decreases.
Yeah.
By decreasing PRF, what does that mean? In 1 second, say here in this case we're transmitting 3 cycles per second, right? So that's a high number of cycles per second. That's the definition of pulse repetition frequency. 1, 2, 3. 3 pulses per second, right? Okay. So when we are imaging deep, that's another way of saying as the depth of view increases, the pulse repetition frequency decreases. So as depth of view increases, this is a very important relationship. PRF decreases. As the depth of view decreases, what's going to happen to PRF? PRF?
Increases.
Thank you. That's why they are in a reverse relationship. So when the system is imaging shallow, PRF is?
Increases, it's higher.
PRF is higher. When the system is imaging deep, PRF is
Decrease.
lower.
Oh,
Higher
so
and
steep.
lower, right? Higher PRF, so PRF increases means another way of saying a higher PRF
Less depth.
PRF decreases is another way of saying a lower PRF, right?
Mm-hmm.
Longer pulse repetition frequency. Longer pulse repetition period would have what kind of PRF?
Shorter.
A longer pulse repetition period would result in lower pulse repetition frequency. Right? A longer period, longer P or P would result in lower P or F. Same way, a shorter P or P would result in a higher P or F. Is this concept and these terminology absolutely crystal clear?
Yeah. You're funny. Everything's inverse. If one's longer, the other's lower. If one's shorter, the other's higher. If one's decreasing, the other's increasing.
Yeah. So now what's duty factor? Duty factor is a unitless number because it's expressed in percentage. It's the actual time when the system is on. So it's 0 or it's 100. It's on or it's off, right? It's that percentage of fraction of time the system transmit pulses.
Duty factor. Duty factor is that percentage or fraction of time it's percentage or fraction of time when pulses transmitting. So that there's another way of saying it. That means it's the on time or is the talk time or it's the transmitting time. That's the duty factor. Is that percentage of time when the system is actually
Transmitting. What is duty factor determined by? Source or medium? Source or medium, come on.
I'm sorry?
What is duty factor determined by?
Source.
Source. Is it affected by the imaging depth?
No.
No. Duty, very good. Duty factor and spatial pulse time, not affected by imaging. Right? So duty factor, which is a percentage, is equal to pulse duration by pulse repetition period times 100. Duty factor is equals to pulse duration by PRP times 100 is equal to duty factor. Oh, right. All right. What time is it?
3:15.